Now, as many of you may have realized by watching how many videos I have on thermodynamics, engineers learn a ton about thermodynamics, and we love it. So, I bet you thought you were done, but no, you're still in the video series because you're having to learn more about free energy change. Now, let's go back to a relationship you should probably already know from a previous video, and this is the Gibbs relationship. And the Gibbs relationship states that delta G, the free energy change, is equal to the change in enthalpy minus the temperature times the change in entropy. So delta G equals delta H minus T delta S. Now, this relationship is true, but there's a little detail I've kind of left off in the earlier videos, and that is this G here has a 0 on it. So these zeros are referring to the reference conditions. And in case you've forgotten, the reference conditions are the concentrations at room temperature and 1 atmosphere of pressure. So basically where we live at every day. Now, the concentrations of these products and reactants, for solids and liquids, this concentration will be whatever the concentration of the liquid is at room temperature 1 atmosphere, or the solid at room temperature 1 atmosphere. But for mixtures and for gases, we define this as 1 molar. So will this free energy change, this delta G, be different if we're at different concentrations? And the answer is yes. And for those of you watching this video, hopefully you're 152 and you know about equilibrium. Equilibrium is going to depend on the concentrations of the reactants and products, because at equilibrium there's an ideal ratio. But we don't necessarily have 1 molar of each compound. So we had to tack on a correction term. And this correction term basically says that the real free energy, the delta G, is equal to this reference delta G plus a correction term. What is the correction term? Well, it's just R times T times the natural log of Q. So the actual free energy change is the free energy change assuming we have 1 molar gases and mixtures and whatever the concentration of the solid liquids are plus this RT. And this Q is going to give us basically the corrections for the concentrations. Now you need to go look at the video on figuring out how to do reaction quotients. But let's say we had just the simple equilibrium of N2O4 gas going back and forth to concentration, or back and forth to NO2. So for this reaction, the delta G is the delta G naught plus R times T times the natural log, or expression for Q in this case, is the concentration of NO2 gas squared over the concentration of N2O4 gas. So what this Q term is doing is describing how far we are away from equilibrium. Now this is going to be a departure from a lot of things we've done with Q. Usually we say Q equals KEQ. This is going to be the one time where we are not equating Q with the concentrations at equilibrium. Q is the reaction coefficient, and it only equals KEQ, the equilibrium constant, if we are at equilibrium. But if we're talking about this relationship, what we're saying is that, well, we're not actually at equilibrium. We're away from it. How much does it change the free energy? Now, let's say you are at equilibrium. So at equilibrium, Q equals KEQ, which equals E to the minus delta G naught over RT. So what happens if we make this substitution? Let's say we're actually at equilibrium. So I'm going to have to erase this relationship. And I get that it's actually ln E to the minus delta G naught over RT. Well, my natural log is going to cancel out my exponential, so I get delta G naught plus RT times minus delta G naught over RT. My RTs will cancel out. I get delta G naught minus delta G naught, which is 0. So at equilibrium, the delta G, the actual free energy change of the reaction, is 0, meaning that neither the products or the reactants are favored. Now, why does that make sense? Well, if you're at equilibrium, the forward and reverse reactions are at the same rate. So it doesn't make sense to say that there's favoritism towards the products or towards the reactants, because at equilibrium, they're both going the same speed. So essentially what this formula is doing for you is saying that, okay, if we're away from equilibrium, what's our driving force? If we have a positive delta G, we're driving towards the reactants. If we have a negative delta G, we're driving towards the products. And Q is going to help give us an idea as to where we are. And this is how you take your delta G naught and convert it to a delta G referring to the specific conditions away from the reference conditions.